All right, physics fans, today we're going to journey further into the land of waves, talking about how waves can be combined. Now, you'll remember from last video that we tried to sell. I tried to sell you the idea that waves are sort of a higher order application of the simple harmonic oscillator. So let's start by just reviewing the simple harmonic oscillator, because this is a Friday video, and on Fridays we have quizzes. So we're reviewing that. So what are the big takeaways that we had from this system? This was our system with Hooke's law, where we had F equals minus kx. So the spring is always pulling our block back towards the equilibrium point. We found that in this case the acceleration was due to, was linearly proportional to the position at every instant, with a extra factor of minus omega squared. Omega, of course, is our angular frequency, which is 2 pi over the total time that it takes for the block to go from the x max to minus x max back to x max. So that's one complete period. T is the period. It's the time it takes to go back and forth through one full oscillation. And we used that with Newton's second law to build up our rule for how the angular frequency relates to the period and, the spring constant, this k, which is what we measured in lab this week, is in units of newtons per meter. It tells you how much force you get per unit that you stretch out your spring, and divided by the mass. So the mass here is in kilograms. All right, so it says for the thing that we developed in the last video was that the energy types trade off in this system between kinetic and potential. So the spring somehow holds the potential energy. You squish it or you stretch it, and it will try to pull you back. So that's potential energy. And the block is holding kinetic energy. So that's the energy of motion. But if you add those two types of energy together, for instance, since your potential energy is related to your position, your kinetic energy is related to your velocity. If you add these two together, you get a constant. So it's always the energy is always trading off, such that at the end points you have all potential energy, and in the middle you have all kinetic energy. And then in these interregnum periods, you have some combination of the two. Then the other system that we learned this week that has the possibility of being treated as a simple harmonic oscillator was a pendulum, where all the mass is at the end. If you have small amplitude oscillations such that sine of angle is approximately angle, so you can't go too far out for this approximation to work, but it does work pretty well for small angle oscillations. In that case, the period depends only on the length of the string. It does not depend on how much mass you put at the end of the pendulum. Okay, so here's a nice little quiz reminder. It says the graph below represents the oscillatory motion of 3 different springs with identical masses attached to each. Which of these springs has the smallest spring constant? Well, let's see. Is there any equation here that might help me? Well, we have that omega equals square root of k over m. Okay, can I look at this graph and get what omega is? Kind of. Remember, omega is the 2 pi times the frequency, or 2 pi over the period. So if we square both sides, we get 2 pi over the period squared equals k over m. And then if we look at that, we would get that t squared equals, I guess it would be 4 pi squared, 4 pi squared over k times m. So t, the period, and the k are inversely proportional. So the bigger my k, the smaller my t would be. So now I can look at this graph and try to figure out which one, how did their periods compare. So if I want to go, they all start at the same displacement at t equals 0. So let's just go ahead. I can going all the way up, all the way down, and back. So there's my t1 for graph 1. Then for graph 2, that's the black line here. We can go all the way up, all the way back. There's my t2. And then my green line all the way up, all the way back, and there's t3. Okay, so we have t1, t2, t3, and apparently t1 is less than t2 is less than t3. And it asks us which one of these constants has the smallest spring constant. So small k would go with a big T, so I guess our answer has to be graph 3. All right, good enough. Now, the other day, so that's your reminder, of course, to take the quiz. The other day we were talking about waves, and we said that waves can travel through many different media. We have mechanical waves, we have light waves, we have matter waves. We are going to be most concerned with these two types. This type is a little bit exotic because it's quantum mechanics. And if you're interested in that, I encourage you to take our modern physics course. Now, the other little piece of nomenclature that we added last time for types of waves is that some waves disturb the medium in the direction that they are that the propagation is going. So this would be a longitudinal, where the squish of the slinky is in the same direction as the squish is moving through the slinky, and so that would be a longitudinal. It goes along the wave. And then the other one is transverse, where the oscillation is perpendicular to the direction of motion. So in both of these cases, V is going like this. Okay, so the key thing to keep in mind here, what's an example of a longitudinal wave? That would be like sound. What's an example of a transverse wave? That would be like light. Sound, of course, is moving through air. So if you don't have air, you can't get sound. Contrary to your Star Wars movies, and transverse waves are moving through the electromagnetic field, so that can move through the vacuum. Now, a point I made in the last video, but which I think is worth making again, is that each point on your oscillator acts as its own simple harmonic oscillator. And if you look at this picture, it looks like you are simply drawing the x versus t for a simple harmonic oscillator once again. So, but the thing to keep in mind is that this is actually at a t equals 0 seconds or something like that. So this is a snapshot. It's not in x and t, it's in y and x. And so instead of describing a period, the period was how long it would take, for instance, for this bump to go all the way down to the minus and all the way back up. So that would be a time issue. Here we have an extra piece of information that we have to add into our mathematical description called the wavelength. And so the wavelength is the distance from peak to peak. Just like in this one, our period was the distance from peak to peak. And so just like we have a variation in time, that was what we described with our angular frequency as 2 pi over the period, we have a variation in space, and that's what we have 2 pi over the wavelength. And so we have the angular frequency here, which has units of 1 over seconds, which is hertz. Here we have k, which we call the wave number, which it tells you something about 1 over meters, and essentially that is 2 pi times 2 pi times the number of waves per meter. Okay, so it's interesting because we have this concept of frequency, which is just the number of waves per second, but we don't usually talk about the number of waves per meter without the 2 pi, and it's just a mistake of history, I guess. Now, the other point that I made in the last video, but which I'm going to be redundant on, is to say that each point on this graph is looking like its own simple harmonic oscillator. So if you look at this point on the graph and you try to plot what's happening versus time, okay, so at this point it would be at your x max. At this point you'd have your string would be going through 0. Here it would be going through minus x max, or minus y max, I guess, in this case. And then here your string would be at 0. And then here you'd be back up to your max. So this is just, if you look just at that point, it's going up and down and up and down and up and down and look just like a simple harmonic oscillator. And in fact, if you put in any individual point, that's going to be the case. So in this case, for instance, we picked your x equals your 1/4 of the way through that wave. So it would be, I guess it would be pi over 2 over k. And if you stick that in, you would get your y equals y max times sine of k. And then if I put this in as my x, I'd have pi over 2k minus omega t. And you can use your trig identities to show that that is the same as y max times cosine of omega t. So you could get a relationship like this on each point on this wave, where each point is going up and down like a harmonic oscillator, but that doesn't really tell you what the wave is doing. The wave is translating this shape over at a fixed speed. So the fact that you have a simple harmonic oscillator at each point doesn't really tell you what you care about. Okay, so just to hammer it home again, it's here's another question, reminder, quiz today. We have the drawing shows the vertical position of points along a string versus distance as the wave travels along the string. 6 points on the wave are labeled A, B, C, D, E, and F, between which 2 points is the length of the segment equal to 1 wavelength. Okay, so a wavelength is where you go from a position over to an equivalent position. So from the peak to the crest is half a wavelength, and back to the peak, that's a full wavelength. From a peak sorry, from 0 back to 0, confusingly, is not a full wavelength because we have that up part of the wave too. So these are the only two ones that are a full wavelength. And so let's see, is A to E or B to F on here? A to E is on here, B to F is not, so that's our answer. All right, now, as we said, the point of these waves is that they are translated over in time and they retain their shape. So how do you describe that in this expression? Well, what's happening is that an equivalent point on a wave retains the same phase. So if you have a point at time equals 0 where the phase, that thing that's in the as the argument of the sine function, that is going, so here for instance that would be pi over 2. This phase for that bump is going to stay at pi over 2 even as the bump travels over. So the way that you describe that is by saying that kx minus omega t, that expression, is equal to a constant. But let's see, can we find out how fast that bump moves? Well, let's try it. If we want, we can try to take the time derivative of both sides of this expression. If k and omega are considered to be constants, and then we have a constant phase on the other side, what we're going to get is that k dx dt minus, and then I take the derivative of this with respect to t, is going to be minus omega, equals, and then I take a derivative of a constant with respect to t, is just going to be 0. Okay, so this is kv, this is the phase velocity, minus omega equals 0. And then you can solve for the phase velocity. The phase velocity is just going to be, bring over the omega, divide by k. Okay, but that doesn't look super familiar to me. How do I get that to look like the expression I already know from middle school, that it's the wavelength times the frequency? Well, I would go ahead and put in the expression for omega. So that would be 2 pi times the frequency. And I would put in my expression for k. K is 2 pi over the wavelength. So 1 over k would be 2 pi on the bottom and the wavelength on the top. And this is just the wavelength times the frequency as we knew. Okay, so just as an interesting side note, you know, if you have that wavelength and frequency, you know that you need a V to be in units of meters per second, and wavelength has units of meters, frequency has units of 1 over seconds. So it's pretty plausible that if you know, take wavelength times frequency, that you're going to get something that has units of meters per second. So it's going to describe some sort of a speed. You know, it would have been plausible that you could get an extra factor of 2 pi or 2 or something like that. But you know, you could go out and measure and see how your waves work, and then try to see further whether you need that extra factor of 2. In your book, they give a nice analysis of a string of tension T, and then they talk all about these, you know, displacing it and trying to apply Newton's second law. I think that this is a good way to try to guess. If you have a string with tension T and a linear density mu, they give us this is their final answer. How could we guess this with dimensional analysis? So we need to get something out that has units of V, something that has units of meters per second. Well, tension is in newtons, so Newton is a kilogram times a meter per second squared. Linear density is in how many kilograms you have per meter of rope, so mu is in kilograms per meter. So if you wanted to build a theory of how fast the phase velocity is going to go on that rope, you need to have something that has units of meters per second. That doesn't have kilograms, so it's pretty sensible. You want to keep the seconds in the denominator. So if I wanted to go ahead and try T over mu, that would give me units of kilograms meters over second squared times, and then if I take mu in the denominator, that would be kilograms in the denominator times meters. So that would give me meters squared over seconds squared. Okay, that's close. And then if I take a square root of that, that is going to give me the square root of meters squared over seconds squared. So that has units of meters per second. So I'm not saying that this is a be-all, end-all way of developing a physical theory, but it is a pretty good start. It's a pretty good start if you're trying to guess something that you don't know the answer to. You can try to combine different quantities that you can measure and try to incorporate them into your analysis. Okay, so just as a second check here, let's make sure that we understand the physical story. It says, Jimmy and Jenny are floating on a quiet river using a giant donut-shaped tube. That sounds like flarf. At one point, they are 5 meters apart when a speedboat passes. As the boat passes, they begin bobbing up and down with a frequency of 0.25 hertz. So they're going up and down 4 times a second. Just as Jenny reaches her highest point, Jimmy is at his lowest point. Okay, so here we have Jen, and here we have Jim. Jen is at her highest point. Jim is at his lowest point. So this distance, they tell us, is 5 meters. But if we want a full wavelength, we've got to go from the highest point of the wave to the next highest point of the wave. So I believe that's going to be another 5 meters. And so the wavelength would be 10 meters. And then they ask us, what is the speed of these waves? Well, we can just use our speed of the wave is wavelength times frequency. So it'd be 10 meters times 0.25 hertz equals 2.5 meters per second. And there we go. All right, now, the reason that we can do so much with waves is that waves can travel through each other. And this is known as the principle of superposition. It's not true in every single theory. There are nonlinear theories, but it's a pretty good approximation for a lot of cases that we're interested in. For instance, in electrodynamics, classical electrodynamics is totally linear. There are some nonlinearities in quantum electrodynamics, although it's a little subtle where they come in. So, all right. When we have 2 waves overlapping, let's say that we have this hump is going to the right, and our other hump is moving towards the left. As they come toward each other, they each have an x position versus t, and essentially to get the total wave, you can go ahead and that is going to be the sum of these 2 waves. Okay, so that's our principle of superposition. It will lead to all of our interesting solutions. Now, one thing to keep in mind is that the energy that's moving through this wave is both, in a sense, kinetic energy and potential energy. The stretch out like this away from equilibrium is potential energy, but as the wave falls down, as it goes like this, there's also kinetic energy that's flowing. So here's a little bit of a confusing example that's going to be very much relevant. Suppose that you have two waves that are traveling in opposite directions, or that in this case we just have two waves that are either in phase or out of phase. If we have two waves that are totally in phase, they add up to give us essentially double the height at every single point. But waves can be either positive or negative. So you can have an amplitude or a displacement from that equilibrium that's negative. So in the electromagnetic field, we consider that as positive and negative numbers. In sound waves, for instance, it would be above and below the normal pressure of air. But if you have one wave that's above and one that is below, one that is a positive and one that is a negative value with respect to that equilibrium, and they have the same wavelength and are exactly out of phase, you can add them together to get zero amplitude. So this I will often refer to as constructive interference. And this would be totally destructive. Destructive interference. And then, of course, the reason why this is a bit confusing is that let's say that you have two waves that are just offset by some wavelength that's not just 0 or pi. In that case, you get some wave that is the sum of the two that is intermediate between them. So it also will look like some sort of a sine wave, but it's not at all points constructive or destructive. So for instance, right here, it's constructive. When our wave is right here, you have more minus than plus, but these are in opposite directions essentially. So it's basically somewhat destructive. So I'm not sure your book uses these terms very much because they don't really apply to every case, but I think they can be helpful in thinking about it. All right, now, as it turns out, we have only been talking about sinusoidal waves, but basically any shape that you can think of could be a possible shape for a wave. You can have square waves, you can have pyramid-shaped waves, whatever. And the way that we can do this is by having a partial differential equation. We call this the wave equation that has many different solutions. So if we basically have any type of linear function with kx minus omega t as its argument, that can function as a wave. Okay, so you can try it. Try sticking this in and using your chain rule, and you will see that this works. Of course, it also works for your y of x and t. That's the one that has been written in your book. That's sort of canonical. This sine of kx minus omega t. And this one, of course, is easy to remember because it already has the omega and the k in there, and you know that it's describing a wave that's moving in the plus x direction. If you put a minus k in there, it could move to the minus x direction, and so on. Okay, now I gave you one homework problem. It's not numbered as 5. It's the last homework problem on your set. That's a little tricky, but I think you can do it. And it says, use the wave equation to find the speed of a wave given by this. Okay, now notice this is actually in the form y equals y max times sine kx minus omega t, where you already can just pick out that y max is 3 times 10 to the minus third meters. You can pick out that your K is 4 radians per meter and your omega is 7 radians per second. So it says find the speed. Finding the speed, using the wave equation is not the easiest way to find the speed. The easiest way to find the speed is just to go, aha, speed is omega over k. So that's your phase velocity, and you could go ahead and just say 7 over seconds times k would be 1 over k would be 4 over meters, and so you should find 7 over 4 meters per second. Okay, so that's the easy way to do it, but that's not what I'm asking you to do in this question. I'm asking you to use the wave equation. That is the wave equation. So you have a v in here, and you're going to use that and find the speed. Now, into both sides, you're going to have to take these derivatives and put them in. So I will help you right now. We will do the left side derivatives. If we wanted to take dy dx, here we would have to take the derivative of this thing with respect to x. So that would be 3 times 10 to the minus 3 meters. And then I'm going to have to use my chain rule. So I'm going to take a 4 inverse meters. Okay, and then I would go ahead and the derivative of sine is cosine, so this would be cosine 4 inverse meters x minus 7 inverse seconds times t. And then if I wanted to get my d squared y dx squared, I'd have to take the derivative again. I'm going to leave off my units for the second derivative. The derivative of cosine is minus sine, so this would be, well, actually, let me, I'm this deep, I may as well keep my units. I'm going to have minus sine, so it's going to be minus 3 times 10 to the minus 3 meters. And then I get another factor of 4 inverse meters, so it's going to be 4 inverse meters squared times sine of 4 inverse meters times x minus 7 inverse seconds times t. Okay, so you're going to put this in, and the key thing to notice is that when you put this stuff in on your left side and your right side, you're going to have a term that looks like sine of 4x minus 7t on both sides that will cancel out, and that will let you use the rest of the stuff to solve for v squared. All right, now the interesting thing about this is that you can do a lot of physics problems with this type of setup, because even if you don't have a problem that's obviously periodic, you can split it into normal modes and do a trick where, for instance, if you have a step function that looks like positive, negative, you can write that as a sum of a whole bunch of sinusoidal functions. So for instance, to a first approximation, it sort of looks like a sine wave, but you can get a better approximation if you add in a sine wave that has double the period, or sorry, double the frequency, half the period, and so there would be your second approximation. And you can get even better if you use something that has triple the period, triple the frequency, and so as you go, you can get better and better approximations. And the trick is that you know how each one of these vibrates, And so you can use this to sort of tease out the dynamics of a more complicated system. So if you're interested in that sort of thing, I believe Dr. Reed does a lot of that over in differential equations. Okay, so notice we've said that the wave solutions add up, and essentially the reason that this works is that we're always using this wave equation, and the wave equation is linear. So if you have two different solutions to the wave equation and you add them together, you just get a new solution to the wave equation, and that's called superposition. One solution plus another solution is a new solution. And that's the idea behind Fourier analysis and all sorts of very nice math tricks that you use in physics. It's also the key to one of our most beautiful physics phenomena, which is standing waves and resonance. So last time we talked very briefly about resonance, but today I want to end with the idea of a standing wave. And here's the idea. Suppose you have one wave that's traveling this way and one wave that's traveling that way. And both of those waves have exactly the same wavelength. Same wavelength, same frequency, same period, but they're traveling in opposite directions. When you have that, and they have approximately the same amplitude too, you can get an amazing phenomena of a standing wave. And what happens is that you have some points where there's always destructive interference, and other points where there's destructive and constructive interference that varies in time. So these points where you always have destructive interference, the 0 points, those are called nodes, and those would be the point on your string that are not moving. And then you have other points that are vibrating up and down. So here's snapshots. Here's a big vibration. At other points, this part of the string would show only kinetic energy because it's moving down, but the string would be totally flat at that point. The points that are going between the big and little, those we call antinodes. Nodes and antinodes. And so in class, I took out a slinky today, and we did some demonstrations with these, but you have seen them, for instance, on a guitar. When I pluck this, the wave is going back and forth, bouncing about, and you can get these. If you set up a node in the middle, it can cause a frequency that's double. So we're going to be talking a lot more about that in class, but the language I want you to have already here is that you have a node and an antinode, and you have two waves that have the same amplitude, same frequency, same period, that are traveling in opposite directions, and that's what's causing this standing wave. So it's like adding this thing plus that thing will give you a new wave that has the same frequency, same wavelength, but it appears not to be moving on the string. It appears to be going like this. Okay, so how do you get that? Well, there are two ways. If you have a clamped end for the string, so assume that I'm like shaking this string up, the disturbance goes down the string, it hits the wall, but if I have a clamp, at that point the wave that bounces back is this essentially acts as a node on the wave, and the bounce back is going to be in the opposite direction. Whereas if I have my string on a slidey pole, if I get the disturbance going down the string and it goes up, it will actually come back in the same way. So a clamped end acts as a node. The open end acts as an anti-node. And so this is going to be important for us, for instance, when we think about whether a musical instrument has a closed end or an open end, or if we have, like on the sides of a guitar, we have both of the sides are clamped, so those would be two nodes. And so we had some fun today shaking slinkies around in class and engineering those standing waves. All right, so I think that's enough for today. You have your quiz, you have your reflection question, and you have your homework to work on for Monday. What have the big ideas of today and this week been? We've been talking about simple harmonic oscillators. Now we've applied them to waves. We've talked about how the waves are the speed of the wave is a point on the wave where the phase remains constant, and the speed of that phase velocity is the product of the wavelength and the frequency. And we've talked about how waves can be added up by the principle of superposition to make new waves. All right, so thanks for watching, and have a good weekend.